Okay, great. So today I'm presenting on an analysis that we recently completed regarding greenhouse gas emission forecasts for electrification of space heating in residential homes across the United States. And first off, I just want to acknowledge our project team, which includes myself, Subrajit Chakraborty, R&D engineer, Mitchell Ditcher, our programmer, Nelson Ditcher, another R&D engineer, and RF Abode, a student researcher. I also want to acknowledge our sponsor, the Natural Resources Defense Council. And I'll talk a little bit later about how we use this cadmium data set for emissions forecasts. And I just want to recognize Peter Gagnon at NREL for assisting us with that. So the objective of our study is to analyze the expected 15-year life cycle operational greenhouse gas emission impacts resulting from replacing a residential gas furnace with a variable speed heat pump in a single family home simulated in locations across the United States. So when we're talking about a gas furnace operating over 15 years, there are various emission sources. So one source is there is some end-use electricity in a gas furnace resulting from use of the air handler fan to move the heat into the building. There are CO2 emissions associated with the combustion of natural gas. And there are also fugitive emissions of unburned methane that we can, and there are various methods to try and come up with a CO2 equivalent using a global warming potential for figuring out how that unburned methane equates to CO2 in the atmosphere. When installing a heat pump, there are, you're increasing your electricity use by displacing the use of methane. The electricity is powering an air handler fan, a heat pump compressor, electric resistance strip heat when the heat pump compressor cannot meet the load. And also there are fugitive refrigerant emissions, which also contribute to the global warming potential as well. So we're gonna, this analysis sets out to compare heat pump emissions to gas furnace emissions in a residential home by region of the US and look at how that differs as we move across the United States. So I'm going to talk about how we did all of this and then share the results with you at the end. So first off, we need to model a residential building because this is actually an hourly simulation conducted over 15 years. And so we need hourly building loads. And so for this, we use some Energy Plus prototype models from Pacific Northwest National Lab. We went ahead and used both the 2006 and the 2018 construction years. And the reason for that is that it's hard to know, we can't really say sort of what the average home in the US is, but what we're trying to do here is a sensitivity analysis to see how does the answer change if you look at an older home with higher heating loads and a newer home with lower heating loads. This was a single family home with 2 stories modeled as on a concrete slab with an attic. And the heating was set to operate to be 68 degrees during the day with a setback to 65 degrees at night. The main differences between the 2006 and the 2018 construction years, you can see here are an increase in insulation levels, a reduction in infiltration of the building envelope, and an improvement in the windows. So the natural gas furnace we modeled an 80% annual fuel utilization efficiency, which is pretty typical. So this is a standard furnace, not a condensing furnace. We sized the furnace to be the same in all climates, although this is a simplification. Changing the sizing by climate doesn't actually change the answer to the analysis because we're calculating essentially how much fuel we're using regardless of the size. And we also included the analysis, the analysis including the fan energy used with heating mode. For the heat pump, we use manufacturer data tables provided to us by Train. For this particular model, we basically, now the heat pump is going to be changed in size depending on where it's located. And so basically what we do is we scale the size by calculating the capacity ratio as a function of the rated value at 8 degrees Celsius. So basically you can see here, so this is the heat pump, it's variable speed. The COP is shown here as the COP at the maximum speed and the COP at the minimum speed. And the COP at the rated condition is 3, which corresponds to a heating seasonal performance factor of 10. So basically, as the outdoor temperatures increase, the efficiency improves. As the outdoor temperatures decrease, the efficiency decreases. Once we get to 18 degrees Celsius, the heat pump switches off completely and you use electric resistance strip heat instead. One little nuance to point out here is that the capacity, generally the capacity decreases as it gets colder outside, but when you get down to colder conditions, the minimum speed of the compressor increases. That's just a function of the equipment. And so you can't run at very low capacities at colder temperatures. So we use Energy Plus auto sizing calculations to size the heat pump. Now, what's a little bit counterintuitive is that the heat pump capacity is actually designed based on the design day cooling load, which is consistent with construction practices in the US. I think the primary reason for this is that when it's very cold outside in cold climates that are heating driven, the electric resistance capacity has to be sufficient to meet the heating load. And so the practical solution is to size to the design day cooling load and then size your electric resistance capacity based on your design day heating load. So this is just, I'll show you later, we ran in 99 cities, but this is showing how the heat pump cooling capacity was auto-sized based on design day temperatures. And this isn't going to be strictly linear because the design day calculation also takes into account humidity. And then this is how the electric resistance capacity sizing increased as outdoor design day temperatures decreased. So this is the heating design day condition, and this is the cooling design day condition. And I show it here for the 2006 and the 2018 construction, so you can see that the capacities obviously increased for older homes with higher loads. So we built this building model, right, that included the envelope and the heat pump equipment or the gas furnace. And we then run the simulation in 99 cities, this parametric simulation. The cities are spread, we group them just to show the results into 6 regions, which I show here on the map. We picked our 99 cities by using the largest city in each combination of state and DOE climate zone. 48 states and 7 DOE climate zones. And then our resolution, most of California is in 1 DOE climate zone. We wanted increased resolution in California, so we also added Sacramento and San Jose. In order to do population weighting for the results for the region, we use the 2019 census data for county population size for the selected city that we simulated. And we present the results as county population weighted averages by region. So the main driver for heat pump emissions is a result of the emissions generated to produce and use electricity. And very recently, NREL released what they call the cadmium data set, which is a long-run marginal emissions rate factor for end-use electricity production. The forecast was produced hourly from 2020 to 2050 by state. And the long-range marginal emissions rate is calculated from the mixture of generation that would serve a persistent change in end-use demand, taking into account the fact that the grid can structurally change in response to increased demand. So for example, electrification initiatives are going to result in utilities building additional grid resources, and there's an expectation based on policy and legislation that those changes to the grid will be an increased amount of renewables like wind and solar, and some natural gas, but for example, not coal, right? We expect retirement of coal plants over the next couple of decades. There is another metric out there called the short run marginal emissions rate that calculates the changes in emissions for the existing grid. And those rates are significantly higher. We don't use them here because we're forecasting long range changes resulting from electrification. And so here we use the long range marginal emissions rate. NREL bases their forecasts on state level legislation passed as of summer of 2020. That's the current forecast that I'm using. So generally they consider it to be conservative because it only takes into account past legislation. It doesn't take into account any type of other additional policies that were not legislated. And then NREL makes available multiple forecasts. And here we use the low cost renewable scenario, which NREL reports is likely to be sort of most reflective of policies that are in place that encourage additional use of renewables. So if we take their data, just to give you an idea of what we're looking at here, if we take the NREL data set and we're looking at the 15-year life of a heat pump. And so if we look over different ranges, for example, we take the hourly data from NREL by state, and we obviously a heat pump will operate at certain hours and not at other hours. But if we just look at averaging all hours, you can see in general that certain regions of the US are expected to have significantly lower long-range marginal emission rates than others. So for example, significantly lower in the Pacific and the Northeast, and higher in the Midwest and the South. I just realized I have a typo there. South. This is Southeast down here. Yes, sorry about that. Anyway, so these are kilograms of CO2 per megawatt hour of end use electricity delivered. And you can see also, as expected, that it generally improves over time. Okay, so another thing we have to consider is how we account for refrigerant emissions in the adoption of heat pumps. Now, because the heat pump is sized based on the cooling demand, the cooling load, the heat pump doesn't contain any more refrigerant than a home with an air conditioner would have. So the question is, how do we attribute refrigerant emissions to the use of heat pumps? If a home already has an air conditioner, the expectation is we're not adding any additional refrigerant to the system by replacing an air conditioner with a heat pump. However, some homes don't have any air conditioning, and adding a heat pump would increase the refrigerant in use in the United States. So what we do here is I'm forecasting out based on DOE 2015 data, the expected adoption of heat pumps in various climates over time. And so the analysis attributes the refrigerant emissions to the fraction of homes that don't already have air conditioning. So that's most significant, for example, in marine climates, so like the coastal Pacific area, California, Oregon, Washington, where adding heat pumps is likely to actually add refrigerant to the system. And then we have to assume a amount of leakage per ton of refrigerant added. And so these are just some details on how we did that. We assume a quarter kilogram of refrigerant per kilowatt of cooling capacity installed, and then an annual emissions rate at 7.5% that declines over time from the year 2020. So we assume better manufacturing and installation practices that will improve with time. And as we move from 2020 forward, the refrigerant emissions will decline over time. The leak rate, we assume, is the same regardless of refrigerant type. And we assume that 410A is in use until 2025, and that a lower GWP refrigerant, such as R32 or R32 blends, are used 2026 and later. And so you can see over here, these are the global warming potentials that we use for those refrigerant types. So we assume basically that the 20-year so for example, for R410A, the 20-year global warming potential is 4,260, meaning that that's the CO2 equivalent. So it's 4,000 times worse than a molecule of CO2. But then R32 is approximately half that. So these are the metrics that we use to compare the refrigerant emissions to CO2 equivalents. Switching back to the natural gas furnace, we assume that this is a pretty straightforward calculation. For every million BTUs of natural gas burned, we generate 117 pounds of CO2. And finally, we have to be concerned about the methane emissions. And so in order to calculate this, we used a very recently published study that calculated estimated production stage methane emissions for each state. And the way that they do this is there's natural gas production basins located across the United States, and the variation in leakage from those basins is pretty significant. And so some states, essentially gas produced and consumed in some states, has higher emissions than others. So we assume we took the data from this study and use these production emissions, which range from 0.9 to 3.6%. And then we also, this is just production emissions. And so we also add 0.5% emissions based on a study for leaks that happen downstream of residential meters. So these are leaks associated with incomplete combustion of the appliance, leaks in your distribution system in your house, and pilot lights. That's all combined in this 0.5% estimate for a total of 1.4 to 4.1%. And then we apply this to all natural gas used by that furnace in a 15-year period. And again, using the same global warming potential metrics, I show here the global warming potential of methane, our best estimate today for the 20-year and 100-year global warming potential compared to the CO2 equivalent. Okay, so that was a lot of methods. Now we're getting to some of the results. One of the things that's going to drive the results is that that warmer climates that can use the heat pump function more are going to have lower emissions associated with them. And so I just show here the heating energy provided by the heat pump mode and the heating electricity consumed by the heat pump mode by region. The balance is provided by electric resistant strip heat. And so you can see here, as you would expect, that more mild climates like the Pacific are able to get more of the heating provided by the heat pump than, for example, in colder climates like the Midwest. And that the percentage that the heat of the load the heat pump can meet improves as construction practices improve. Slightly, it's not hugely significant because the heat pump size also drops in the newer construction. Okay, so here we see the comparison of the 20-year global warming potential. So on the darker colors here, so the black, the black on the bottom is the CO2 electricity associated with the air handler fan. So you can see, for example, it's a small difference, but the heat pump uses more electricity for the air handler fan because it runs at a lower temperature differential than a furnace, which you would expect. The dark yellow is the natural gas combustion. The dark blue is the electricity consumed by the heat pump compressor. The light blue is the electricity consumed by the electric resistance heat. And sorry, I should preface this by saying this is for all 99 cities, population weighted for a US average. The yellow is the GWP20 natural gas leakage converted to a CO2 equivalent. And the little bit on top here is the refrigerant leakage converted to a CO2 equivalent. And so you can see here the emissions drop by about 60% for the home as a whole with newer construction, as you would expect, because we just have less heating energy that needs to be provided. Just showing a similar relationship here briefly for the 100-year global warming potential, the impact of the refrigerant leakage and the natural gas leakage is less significant on a 100-year timescale. And now here, if we just want to look at the actual CO2 emission reduction, so this is only the burning of the methane and the electricity generation that we compare here. We can see CO2 emission reductions by region. This is by year of heat pump installation. So you can see here, and this is over 15 years. So this is installed in 2022 and operating for 15 years. This is installed in 2036 and operating for 15 years. So we see emission reductions increase over time. And we can, this is the overall US, and then you can see the difference by region. For example, the highest reductions being seen in the Pacific region, the lowest reductions, but still very significant, being seen in the Midwest. And this is perhaps one of the most interesting results, even though the absolute emissions are quite different, the reduction of emissions between 2016 and 2018 construction are extremely similar. This is the same calculation, but based on the GWP20 emissions. So now this wraps in the methane and the refrigerant leakage over a 20-year time scale, which increases the expected emission reduction. And then finally, the GWP 100 emission reduction, which is the same analysis, but looking at a 100-year time scale instead of a 20-year time scale, which lands essentially in the middle of the previous calculations. And so just some final points. The analysis shows significant emission reductions forecasted in all regions. The results are highly sensitive to the forecasted emissions for end-use electricity generation. So in this case, we use those long-range marginal emission rates that were just recently generated and made available by NREL in the past few months. I also want to point out that one thing that I see coming in the future is improvements to heat pump controls that could allow us to run heat pumps during times when more renewables are available. And that none of that is included here, and that would potentially improve emissions reductions. I also want to point out, we assume in the results that all the methane leaks are eliminated with replacement of the heat pump. A fraction of those methane leaks may not be eliminated if there are other, like the ones associated with heat pump themselves. Any unburned methane inside that heat pump would certainly be eliminated, but any leaks in the distribution of the home or in the local distribution network in the neighborhood would potentially still remain if the entire home or neighborhood is not electrified. However, the vast majority of emissions are associated with production processes and would be eliminated in the heat pump replacement. But there's some nuance there, so I wanted to point that out. And that's all I have. Any questions?
Great, thanks, Theresa. Yeah, so if you have a question, feel free to raise your hand or put your question in the chat box. We have a few minutes. to get those answered.
It's like Holly has a question.
Yeah, thank you so much for this. This is really impressive. And also, I mean, it's a lot, but you've put it in a very easy to digest format. So really appreciate that. I actually work for a natural gas company out of Portland, Oregon, and we've seen similar information, but we've put a lot of energy around the commercialization of a gas heat pump for water heating, but also there's a space in water heating. And so I'm wondering, have you looked at or considered doing this analysis with gas heat pump technology?
Yeah, we've actually had some entities reach out and ask us that. We haven't had time to do that yet, but I understand there's quite a bit of interest in that. Maybe if you want to just send me an email about that specifically, I can follow up with you on that, because at this point we put a lot of work into the whole framework of all this. So now we are getting to the point where in theory we could drop in, mechanical system C, boom, and run the results again. But
and then is it also, that totally makes sense, and that's really exciting and hopeful. The US average 20-year global warming potential, I feel like that one's like especially crystal clear to see. Is it possible to get that for different regions? You showed us the rolled up all US, the yellow and blue.
Oh, yeah, it all exists. It's just sort of like what people find most useful. So you mean like so this chart is then boiled down into these percentages, but you're interested in this specific chart by region.
Yeah, but I'll send you a note offline.
Yep, that's available. What we want to do is publish this, and then actually what our end goal is to publish this and then actually have like a website where people can go download the parametric simulation and the model and then run additional scenarios is a possibility, and actually analyze the data themselves if they want. There's lots to look at that comes out of this.
Thank you.
So I just put Theresa's email in the chat, so you can access that. And then someone had asked about, will these slides be available? And I know this is kind of a practice presentation in a way. We're going to be doing a more detailed webinar on this actually on April 20th at 10. So if you want to sign up for our newsletter, you'll get an announcement about that webinar. So that would have more detailed information probably, and more final, kind of a more final presentation, Theresa, is that?
Yeah, well, we plan to hopefully, this is a first run through of this today, so we'll use, if anybody has any feedback specifically on any more questions or ways to improve that, we'll try and incorporate that into our presentation on the 20th. But overall, all the material presented will be the same. Maybe a little smoother on round 2.
And then we have a chat question from Jay here. Realistically, we don't, yep.
Jay observes, I mean, you can see here overall for the entire Pacific region, which includes California, that 95% of the heating can be met by the heat pump. And so there's just a question as to, I think particularly in California, you could forego the electric resistance heat completely. The main issue would be your ability to recover from a setback. For example, if you're on vacation and you don't heat your house and then you come back and it's 55 degrees and how fast do you want it to be 68? So there's just some sort of comfort decisions that might need to be considered, and how people are sort of used to interacting with their heating system.
Great, and it looks like Tom had a comment as well in the chat. Are you able to see that one?
Yeah, so Tom says, we used a higher efficiency heat pump, but lower efficiency gas appliances. That's a fair point. The analysis would be different if we use condensing gas furnace. So that's another potential mechanical system that could be modeled. And so that's, yes, and Brian Davis points that out as well. So that's certainly a legitimate comment. I agree. However, I as far as which one wins, I don't know that would be a significant enough difference to change the balance in favor of a gas furnace. But anyway, we're not from a research center perspective, we're trying to be very transparent about the analysis that we're running. And then we also want to make all this available so that additional analyses can be run. We're not essentially trying to, the goal isn't to favor one technology over another.
I would say, at least here in California, the heating is really so little compared to the rest of the country that that difference in the efficiencies probably wouldn't move your needle too much.
Yeah, and the marginal emissions factors, there's, I think we could debate that significantly to the end of time. But I'm happy to refer you to NREL's cadmium website. They have some very detailed reports that list all of their assumptions and how they get there. And my opinion is that it's fairly conservative, but you're free to reach your own conclusion on that.
Great. Okay, well, we need to wrap up at this point, and we'll pass the presentation over to Yoni. Thank you, Theresa, and thank you all for your great comments. We'll have an opportunity at the end, probably for a few more minutes of questions if you have any remaining.
I'm going to stop sharing my screen. How do I do? Where's my button? Oh, here it is.
Can you see my screen okay?
Yeah, it looks great.
Okay, super. My name is Yoni. I'm a data scientist with the Center for Water Energy Efficiency, and today I'm going to be discussing some of the work we've been doing to estimate the water use of evaporative coolers from observational data. So this is just a little outline what I'm going to talk about today. I'm going to give you a problem statement. I'm going to go into some methodology and results, and then I'm going to discuss the next steps for this project. So our goals are twofold. First is to estimate the average water use, water consumption of evaporative cooling systems. And part two is to be able to identify homes that use evaporative coolers. So a little bit about the data we have at our disposal. We have monthly water data, hourly energy data, hourly weather data, and property characteristics for a small Southern California water district. And want to emphasize that this is account level data for single family residences. So for an individual home, we know how much water they use in a given month and how much energy they use in a given hour. And then on top of that, we have this cooling indicator, which we got from the county assessor's office. And that tells us what type of cooling system each home in our district is using. And I want to dig a little deeper into that because it really provides the basis for our analysis. Our homes really break down into two classes, class 1 and class 3, and those correspond to homes that have refrigerative central air and homes that have evaporative non-central cooling systems. So we are lacking in some things that we would ideally be able to test, such as these evaporative cooling central systems. There were only 8 homes in our data set that had that information, and that's just not really enough to do any meaningful statistics with. So keeping that in mind, we have two classes of homes in our data set, and those are the things we're going to be comparing. So these are some of the modeling and data considerations we made over the process, the analysis. We had to worry about irregular occupancy, extreme values. Sometimes the utilities data was just like a little bit wonky. Our samples are definitely not IID, so we had a way of addressing that. And then we needed to decide how we wanted to deal with the non-normal response. And we tested a couple different methods, but we ultimately, for our use case, settled on not transforming the response and using just a standard linear model, as that's going to be much more interpretable for our stakeholders. So now getting a little bit into the methods that we used. This equation up here is essentially the foundation of our analysis. What we really tried to do is look at the relationship between average daily temperature and average daily water consumption in any given billing period. So CIM is the consumption per day, average daily water consumption for a premise I in month M. And then the two major modeling components were the heating degrees, so the average heating degrees over that billing period, and the average cooling degrees over that billing period. And our hypothesis is that homes with evaporative coolers are not going to be terribly distinguishable from homes without evaporative coolers during the heating months with high heating degrees. But months with high cooling degrees, we should see an increase in water use relative to homes without evaporative coolers. So the results from that are shown here. B1 is the heating degree component, and B2 is the cooling degree component. And the results support our hypothesis, which is to say that there's not a distinguishable difference between homes with and without evaporative coolers in the colder months. And there is a slight difference between the two home classes in the hotter months. And so translating this to actual water use over the course of a month or a day, these values are in liters per day per degrees Fahrenheit. So we can take a typical year or month and translate the degrees Fahrenheit in any given day to tell us how much water we think a home is with an evaporative cooler is going to use. So this plot shows exactly that. And then we can use psychrometric calculations to try to estimate approximately what home size the evaporative cooler here would be cooling. And these results correspond to about a 100 square foot area of evaporative cooled area based on those calculations. So that's the main portion of our analysis so far. Our next steps are to actually improve the current method we have to impute that cooling indicator when it's missing. Not all of our stakeholders are going to have access to those county assessor data sets. So it'd be very helpful to them if we could, if we have a method that'll let them figure out exactly which homes have evaporative coolers and not. So our current method to do this is actually based on a very similar idea to the previous method, except now we're going to be modeling, C is going to be the consumption, the daily kilowatt hour per square foot in a given premise in a given day. And we're going to model that based on the heating degrees in that day and the cooling degrees in that day. And we're going to actually we're going to perform this analysis for each individual home over all of the data that we have. All of the energy data, and we're going to use the parameter that pops out from that analysis as a predictor in our classifier. So using that cooling day component predictor along with a bunch of other property, energy, and water variables in a random forest classifier, which is just a easy off-the-shelf algorithm, yields 82% accuracy on test data. That's not really very good. So we're hoping that we can, improve our methods, find some other predictors, maybe change our classification method and improve that number. But the most important thing to me right now from our results is that the major predictors are home vintage, home quality, home size, and mean daily water use. And so energy so far has not even been a useful predictor for that. And I find that interesting in and of itself. So that's everything I have for you so far. Thanks for your feedback. I just wanted to emphasize that I don't actually have a lot of background in evaporative cooling. And if anyone here does, I would really like to talk to you just to confirm that some of the assumptions I've made throughout this process are reasonable. So yeah, I'd love to hear from you if that's the case.
Great, thanks so much, Yoni. So I put his email is also on the screen. I put it in the chat. Feel free to contact him directly, but we do have time for some questions. So feel free to raise hand or put it in the chat, and we will get those answered.
Yanni, I'll just say I've spent 10 years testing evaporative cooling technology. So if you want to connect for a half hour, happy to do that.
Awesome. That'd be helpful. I'll email you. Thank you.
Great. We can also take any questions that hadn't been answered for Theresa's presentation, or we can give you back 15 minutes of your Friday.
I have one. I don't want to steal. Yeah, I don't want to steal everybody's 15 minutes. So feel free to peace out. But it's for Theresa. I was just curious how much of an effect having the hourly marginal emissions data makes versus if you just use some of the kind of rolled up numbers for annual marginal emissions that I think are more commonly used in, higher level studies looking at generating those marginal emissions predictions. Like if you just apply the average for the year or for the month instead of the daily, the hourly load profile, the marginal emissions data, how much of an impact does that have? Do you have any feeling on that?
We didn't do that. I mean, that would be fairly straightforward. That's an interesting suggestion. I mean, we were really focused on the hourly analysis just because, heat pumps are going to run more, at night and early morning and during times when it's cold and maybe not as much solar available. So, so we were really excited to be able to do the hourly analysis, but it'd be an interesting comparison. The answer is, I don't know.
Yeah, I'd be very interested to see that because we have the same. We're collecting a bunch of measured load data from commercial buildings from the heating system nationally at the moment from hundreds of buildings, and as you can imagine, the hourly load profiles are very diverse and radically different from a residential system with buildings operating 24 hours a day and heating loads in the summer and everything like that. So I'm just kind of curious how much of an impact having the hourly data does affect these results compared to just like these annual roll-up data that is more commonly used because people don't have hourly load data to
Is there a
plug in.
specific data set for that you'd recommend for the United States by state in terms of like averages?
I think you could just average up the ones from NREL from Cambium and just blanket, use the exact same data source, but just like take out
like if you didn't do the analysis to this level, where would you land?
if you only had like the annual heating load data for the building or something, would it make a huge difference for this particular load profile? It should be
if we get
pretty
the same
trivial
answer
to do.
And I just spent months of my life running Energy Plus models, Paul. I don't think you will, but
I'm confident you won't get the same answer, but
right.
Yeah. And thanks again for the study. It was super interesting.
Just to chime in, Paul, there is a recent study that has been done, and I've been working with Theresa and helping her with this study. There are some studies that have been recently done that they do a comparison between annual and hourly. Just one done by authors in Italy, and these are very recent studies that point to the fact that the importance of doing an hourly study because the demands change so much, and also the source of energies that the grid uses changes so much. So they saw a huge difference between like annually rolled up averages and the hourly. And I mean, if you
it would be fairly straightforward to compare though, just to motivate the importance if that's what we expect to happen. But,
yeah, I'd love to see that analysis, and Superjit, if you have those papers, I'd be very interested to read them as well, because it's been a concern of mine for a long time that a lot of the marginal emissions the forecast generations for how the grid will change don't actually account for the hourly load data that's specific to things like, you know, heating, electrification, and the impact of that on the grid. Like the reality is you can't serve a residential heat pumps load with a solar PV system in most climates for most of the time, right? It's just the wrong time of the day. So I'd be curious to see now that we have the data courtesy of Theresa and her team, how much of a difference it actually makes for a residential load profile.
Well, we have to credit Enmo with that emissions forecast data. We did not make that.
Right.
We just used it.
Right, but you did all the Energy Plus stuff.
Yeah, that's right. Yeah, it would be pretty straightforward to do that at this point. So I'll make a note of that.
Great, thanks.
Okay.
Great. And Paul, I just sent you Superjeet's email if you wanted to follow up with the email.
Oh, great. Thank you very much.
About you, Rhett. All right. I don't see any other hands up. Oh, wait. Here's somebody. Oh, yeah. Tom, go ahead.
I have an actual hand up.
You have an actual hand. I haven't seen those in a while.
I wanted to thank you guys so much for this. My only concern with this is the assumption that everybody's going to get rid of all gas, even if a heat pump could take over a furnace. I have 6 appliances in my house and probably would only get rid of 4, even if they were ever better electrically than they are gas. And so the assumption that you're going to get rid of all of the distribution methane leaks is probably wrong assumption if somebody still wants to cook with gas or run their dryer or whatever. And so it would be nice to see maybe this same study only have it stop at this is the difference between these 2 things at this site, just so that we could see what's going on. Very close to what your last study was like, talking about today, what our marginal emissions are today, that a furnace is actually lower carbon in our service territory, at least, than a heat pump is right now. And it'll be 5 to 10 years before it's less. But this study at least showed us what would be over 15, and I appreciate that. But I feel like it might have been just a step too far to say you're going to eliminate all gas.
Yeah, if you actually, I don't have, yeah, I want to look into that a little bit more. If you do look at the breakdowns, the local distribution system leaks and the leaks downstream of the meter are quite small. Like the ones that would be left inside the home are quite small in comparison to production level leaks. But I agree they're non-zero. So yeah, we'll give a little bit more thought of how we handle that. But that's why I sort of put that caveat on at the end. We have other research going on at the center where we look at sealing natural gas, low pressure natural gas distribution pipeline networks so that we can overall reduce leakage for the remaining appliances. So we're very aware of that concern, because if you have the gas distribution system pressurized at all, right, then those leaks are going to remain. So I agree with you on the point. It's just a little bit difficult to figure out how to what specifically include in the analysis and how much data we really have to be able to disaggregate that. But yeah, we're working on that.
Well, thank you so much.
Okay.
I appreciate all your work.
Thank you.
And Theresa, we have one more question that came in from John in the chat about life cycle costs.
We have not done that. It's very complicated because of all the utility rate structures that vary all over the US. So we don't have the capacity at the moment. We didn't have, yeah, we haven't done that, but that would be cool.
Any volunteers? Yeah. Awesome. Well, on that note, thank you everyone for coming today, and thank you to our presenters. We hope to see you next week. We'll have two other topics of interest. You'll get an email coming out on Tuesday, probably announcing those. So hope to see you next week. Have a great weekend, everyone, and thanks for joining.